Um, Welcome to this session. We have our next speaker is Hassani, who is a assistant professor in the Department of Electrical and Systems Engineering. He has also at UPenn, and he has many other appointments in statistics and data science and computer information systems. So
thank you. Hello, everyone. Thank you all for attending the visit day as well as this talk. So the talk will be about neural compression, and I'd like to start with giving you an overview of what neural compression is, why is it successful, and what are the fundamental questions we should ask here as information theorists or data scientists. So first, a word about what lossy compression is. So lossy compression means that we want to, given a data point or a data set, we want to compress our data point here, x, into bits, such that later on we can decompress using the compressed bits, these bits into some other lossy version of our original data point, which we call x hat. Okay, so that's essentially the overall architecture or story here. And so here we are working in regimes where the number of bits is much, much smaller than the actual size of the data point or the image that we are working with. And as a result, the reconstructed data point, the reconstructed version, is quite lossy. And as a result, we can talk about the distortion between the original data point x and its reconstructed version x hat. And this distortion has been measured in various ways. Maybe the most common metric would be the quadratic distortion, which is essentially the norm of the difference, the square of the norm of the difference. That's the most common metric. But there have been other metrics, for example, perceptual-based metrics, as well as PSNR, and so on and so forth. Now, neural compressors refer to cases where the compression and decompression operators here are based on neural architectures whose weights are trained using some data sets. On the other hand, we can talk about more traditional kind of compressors, such as JPEG, where the compression and decompression operators are based on the Fourier transform or the wavelet transforms of the input image. So that's basically the picture here. Now, so I have two pictures here. The one on the left is a reconstructed version of an image, an original image, which was first encoded into around 4,000 bytes using a neural compressor, and then reconstructed using a neural decompressor. And the neural nets were trained using some standard data set. So that's the image on the left. The image on the right is the same scenario, but everything is done using the JPEG algorithm, which we use every day. Now, if you look, the image on the left is better perceptually to us as humans compared to the right. So in terms of the common perceptual metrics, the one on the left has a much better performance. Also, in terms of some other metrics of distortion, for example, quadratic distortion or PSNR, the one on the left is much superior to the one on the right. And this is, even though they use the same number of bits, actually the one here has used a slightly smaller number of bits for compression. And this showcases essentially the success of neural compressors. So if I want to be more formal here, so these plots compare the performance of deep neural net-based compressors compared to traditional compressors such as JPEG or BBG. On the y-axis, we have PSNR, the higher the better. And on the x-axis, we have the rate. And as you see, these neural compressors significantly outperform traditional compressors. And this plot is for 2 years ago. Now we have much more powerful compressors that go even beyond these kind of DNN-based compressors. So longest story short, neural net-based compressors have achieved tremendous success, at least on images, compared to the traditional methods. And so one intuitive reason on why these neural compressors work well, at least on images, is that they have the ability to generate images. So here, for example, once the neural compressor figures out that there should be grass here on the green side, and it realizes it through the compressed bits, then it has the ability to draw grass, okay? And the details of the grass are also extracted from the compressed bits. Whereas for JPEG, since JPEG doesn't have this ability to generate, so it's based on the wavelet transform and removing high order frequencies. So you see that there is a lot of distortion, at least on this grass. So this ability to generate is a distinguishing factor, and the ability to generate is learned from data, actually. Right, so when I started to work on this area of neural compression around a year ago, I actually talked to a senior information theorist who happens to be a a faculty here at UCSD, and he asked me this very interesting question. So the question was, didn't information theory actually solve this problem like a few decades ago? But that's a very good question. If I want to rephrase it in another way, the question is, what's new here? Okay? What can these learning-based architecture capture that couldn't otherwise be captured by classical methods such as information theoretic methods or, let's say, signal processing methods? So to answer this question, let me take vector quantization, or the so-called k-means algorithm, which is one of the famous methods for data compression, and see how it performs. So we are working with some real-world data set, let's say a data set of images. A naive way to implement things would be to take each data point, and then, so each data point would be a tensor of pixel values. You vectorize it into a very large vector. So D here is very large. This is as big as the number of pixels used in the representation of the image. So that would give you a point. So each image would be a point in this high-dimensional Euclidean space. You have a data set of points, and essentially your goal is to find, so compress these points to other centers such that this kind of distortion metric, here's the quadratic distortion, is minimized. So if you write this distortion as an empirical sum over the data points, essentially you are solving the so-called k-means problem or vector quantization. So the goal is to find these red points, the centers, such that the average distortion, the sum of the square of the distance of each data point to its closest center, is minimized. And your goal is to find those red points, those centers. Okay, so assuming that you can implement this, it's a bit tricky to implement k-means in these high-dimensional data sets where the number of centers is very large. I'll talk about that a bit later. Assuming that you can implement this, if you measure the quality, the distortion quality, you will see that the distortion quality is quite high compared to, let's say, neural compressors or JPEG. And there are a few reasons for this. Maybe the most important reason is that the structure of the data is somehow neglected. So the k-means objective is what? Is the sum of the distances of every data point to its closest center. Somehow it loosely captures the geometry of the data. What do I mean by geometry? So here, each data point is represented in a very high-dimensional space, just all the pixel values, right? Whereas we know that images have a lot of a structure, right? So in other words, images essentially lie on some low-dimensional manifold. And the actual dimension, the local dimension of this manifold, is much, much smaller than the dimension of this pixel representation of the image. And this geometry is very loosely captured in this k-means objective. So we really need methods who could directly target for the geometry in the data and exploit that. If you run k-means, these centers that we find by just naively running k-means do not even fall on this manifold. So you would get centers that look like mixtures of images. I mean, perceptually, they're not even good. That's the problem. So geometry is neglected. The other problem is that we are working in regimes where we want to compress our images to, for example, at least 100 bits per image. So we have 100 bits. This means that we need to work with 2 to the 100 centers. So we have so we need to solve a k-means problem with 2 to the 100 centers, and these data sets are already very high dimensional. Well, I mean, this essentially makes k-means impractical because 2 to the 100, we cannot really do it. So that's the other problem, is that the number of centers, if you want to just run naive k-means, would be very, very large. Okay. So these are the challenges here of classical information theoretic methods. And let's see how learning can come into the play here. So we had 2 challenges, geometry and number of centers to be very large, complexity. So geometry, we typically think of geometry, at least in the learning literature, as kind of a map, G, from some low-dimensional space to a high-dimensional space. So RD is the actual pixel representation of our image, but RK is the low-dimensional nature of the image. And this mapping G is essentially a generative mapping, which takes as input this low-dimensional kind of vector and essentially gives you the high-dimensional version of the image, right? So the image of G, okay, so computed over all the possible values of Z, would be essentially this low-dimensional manifold of the data. So it's represented in this very high-dimensional space, but it's actually a low-dimensional object because of this structure that you see here. Well, the challenge here is that G is very complex and completely unknown, right? We don't have an analytical map that gives us G, right? And that's exactly where learning comes into the play, because what learning proposes is to actually learn this mapping G from data. Okay, so the way we learn these generative models, well, there are various ways now, given the recent advances. But one way is through autoencoding kind of approaches where alongside with G, you also learn its inverse map. So G was from low dimensions to high dimensions. Then you would also learn its inverse map, F, which encodes or represents X through this representation vector G. Okay, and then you learn both of them at the same time. Okay, the way you do it is that you parameterize both of these using some neural networks, some neural architectures, and then you train the weights of these neural architectures such that, first of all, this loop is closed, and second of all, it fits very well to the data set that you're using. Okay, so you train these weights, and that gives you the mapping G, which on the other hand also gives you the geometry of the data. Okay, so far this is just generative modeling. We have very good ways to do that. Now, so that's how you essentially capture geometry. The other challenge here was the complexity. The number of centers was very large. So the common practice in communication, in communication or signal processing is that you don't really try to find the centers first and then store them. The way you do, you go around this challenge is that you find encoding and decoding operations, which are very efficient, and they directly give you the bits. So you don't even compute any centers here, you directly compress your images, for example, into bits. Now, the way in neural compression this is done is as follows. It's quite simple. So you essentially quantize the representation vector into bits. Now, this quantization operation is itself a very complex operation, but that's essentially the picture here. So end to end, you have a neural compressor looks something like this. You have encoding operations, decoding operations. The encoding gives you a representation which is quantized into m bits, and these bits are reconstructed into a reconstruction vector x. And this end-to-end, so these neural nets here, along with the quantizer, are essentially trained using the here available data set in order to fit the data set and minimize some distortion metric. Okay, so I made it too simplistic here. So there's actually some serious engineering going on. So this is one of the state-of-the-art neural compressors from this paper that I recently read. So you see that the encoder and decoder have a few convolutional layers as well as attention layers. And the quantizer itself is quite complex. So it first estimates a posterior on the distribution of the representation and then uses this information theoretic variable length encoding operation to essentially quantize it. So there's a lot of interesting ideas going on here. Well, longer story short, this is a quite active area of research. Every day you see papers that try to essentially improve the quality of neural compressors by proposing new architectures. And by improving quality, what I mean is that you want to essentially minimize the distortion given some certain budget on the rate. Okay, and this brings us to the fundamental questions that data scientists or information theorists could essentially study here. So the first natural question is, what are the fundamental compression rates that we can achieve here on these very massive kind of data sets, high dimensional massive data sets? So here what I mean is that, so given a specific budget on the rate, so if you want to compress your image into, let's say, 200 bits, what's the minimum distortion you can achieve here? The minimum value of the, or the best quality that you can achieve. And here, by fundamental limit, I mean over all the possible compression or decompression methodologies, not just neural compressors. Okay, so we're talking about fundamental limits. Well, when talking about fundamental compression limits, information theory provides a concrete framework based on the rate distortion formulas to answer this question. However, the rate distortion framework is based on knowing that data comes IID from some known probability distribution, and you can optimize mutual informations and so on. None of these, so these are all very challenging in the context of big data sets. The problem here is that in these large data sets, the only thing that you have access to is just data, a bunch of high dimensional vectors. You don't have any probability distribution to work with. You cannot, definitely cannot compute any mutual information because things are very high dimensional, so probabilities are very complex and so on. So these are the challenges. Computing even the rate distortion functions for these real world data sets is itself a very, very complex and important challenge. So that's question number one, fundamental limits. And the next natural question is, once we know these fundamental limits, well, what do neural compressors do compared to these limits that we have? Why do we want to study this question? Well, so this is from a recent paper that we have. So and this is over the MNIST data. So MNIST is probably the simplest data set you could consider for compression. So this is the green curve is the rate distortion function. So the value is so the rate distortion is precise here, and the red is the performance of neural net compressors. And you see that there's a sizable gap between the two. So why is theory useful? Because theory, and as we will as I will mention very briefly, theory would tell us what are the limitations with this neural compressor. So this is the best achievable neural compressor, state of the art. So what's the problem here? And essentially, how can we essentially try to close this gap between the two? So these are the fundamental questions that we've been thinking, and these are some of the results that we have been developing in the last a year or two. So let me very quickly, so it's 1 minute for each result. Let me just explain. So for the performance of neural compressors, as it is typical in theoretical kind of results, we start with the simplest possible architecture here. So the simplest possible architecture would be to consider a one-layer encoder, one-layer decoder, and then the quantization here would be just sign, right? So a very simple kind of architecture like this, everything one layer, the nonlinearity is sign. And for this architecture, we can write the distortion function. We can try to optimize this distortion function in terms of the parameters of the neural nets that we are considering. So all these questions, we've been able to find precise answers for theoretically for this problem, one-layer neural nets. And we have been able to, so for the Gaussian sources, obviously, and then for the Gaussian sources, we also are able to compute, and that's like a well-known result, we are able to compute the rate distortion curve for these kind of Gaussian sources. So we know what the fundamental limit is already for these problems, and we know the fundamental limits of learning with two-layer autoencoders. Through these theorems developed in this paper, we also know, we can also show that gradient-based algorithms converge for this problem. I mean, these problems are highly non-convex, so it's not easy to show that gradient descent algorithms converge, but for this problem, actually, we can develop tools to prove it. So the main message here is this. So the blue curve is the performance of neural compressors, and the orange curve is the fundamental limit, the rate distortion function. And there's again a concrete gap between the two, but by analyzing the features, we now know that this gap is really fundamental, meaning that there are elements of compression that these neural autoencoders do not really capture. So the difference for those who are familiar with these kind of quantization methods, the difference is between a scalar quantization and vector quantization. So neural autoencoders do not really do any kind of vector quantization or let's say typicality, but they are not able to do that. At least these simple kind of architectures. So that was the first result. And then secondly, did you do something to stop it? So I mean, these results we can also find. So our theoretical predictions are also exact if you use like CFAR or real-world data sets. So for the second result, so we can compute the rate distortion function for real-world data sets. So well, the rate distortion function is very complex for these high-dimensional data sets. Mutual informations cannot be computed. Probabilities we don't have. But it turns out that we can essentially use a very interesting duality relation developed by Dembo and Kontoyanis in 20 years ago. And using this duality, we are able to find precise estimates for the rate distortion function. So that gives us an algorithm. Let me not go through this, but what's important, so for Gaussian, everything is exact, and this is an easy check. But again, we will see that there is, as I mentioned, there is a concrete gap between what neural net compressors can achieve and then the rate distortion function. And we believe that this gap is again because of the difference between a scalar quantization and vector quantization. So that's what we are actually working on right now to be able to close this gap. But it's very non-trivial as it turns out. Right, so let me stop here. Thank you.
Thanks for the great talk. Sure. I think we are going to hold questions until the break. Or we can have one question while Arya is setting up. Maybe. Sure. Yes. Right.
A very quick question. For the simplest architecture for the audio encoder, maybe I missed something here, but how does that compare with what people are using with the neural tangent kernels for autoencoder purposes?
Right, so that's a very good question, actually. So neural tangent kernels, so the basic idea there is that, so you have a feature vector, and then you have so they use it for classification. You have a feature vector, which is a very wide feature vector, and then you would use that, you would train that feature vector using the data for classification. So here we don't have, so here you want to compress your data into something which is of a smaller dimension. Rather than very, very wide. Okay, right. So that's the, and that brings new challenges in optimization and so on. Okay. Thank you.
Thank you.
Okay.